Okay, now we're talking about rotational dynamics. Now, first of all, let's quickly review over rotational statics. Rotational statics are objects that are either at rest or constant speed. In both those cases, there is no acceleration. So in a rotational world, the sum of the torques will equal 0 if an object's at rest or at constant speed. In a linear world, straight line motion, oftentimes called translational, the sum of the forces are going to equal 0. So that's what happens if we're not accelerating. So now let's talk about objects that accelerate. Now, for the linear world, we use the most famous equation ever written, the most powerful one. The sum of the forces equal m times a, Newton's second law of motion. Excuse me. And again, that's an importantly powerful equation in the world, and it simply governs. Now we're talking about objects that are accelerating, so we need to make sure that we make that correlation. So therefore you have sum of the f's equal m times a. Up here a was 0, so therefore ma is 0. Now in a rotational world, okay, in the angular world in which we're moving, now what's going to cause an object to spin? Objects are going to spin because of torque. So there must be a net torque on something in order for it to spin. Now, it's very similar to this equation. This is Newton's second law for rotational stuff. The sum of the torques are going to equal, well, remember in the rotational world, it's not mass, it's moment of inertia. Moment of inertia tells you how easy something spins. Remember, mass tells you how easy something accelerates in the linear world. Moment of inertia tells you how easy something accelerates in the rotational world. And then, of course, the acceleration in the linear world also has a corresponding acceleration in the rotational world, which is alpha. So the sum of the torques equal I times alpha. This is the moment of inertia. Again, depends upon the shape and how the mass is distributed. And this is angular acceleration. And we have a bridge equation. A is equal to A is equal to alpha times R. So that's a bridge equation. Let's rewrite that. A is equal to alpha times R. That's a bridge equation that allows you to bridge and compare linear A and rotational A, rotational acceleration. So this is a way to bridge between the two different topics. Okay, let's look at a sample problem and let's apply this. Let's take a cylinder, and it's going to pivot about a rod in the center. We're going to make the rod frictionless, and what we're going to do is wrap string around it, and then we're going to pull the string off. Let's pull the string down this way. And we'll apply a force down there. This is going to have radius r. Let me see what else I need to give you. Let's tell you that the mass of the cylinder is 1 kilogram, and let's make r is equal to 0.5 meters. So let's go through that. Now, so what's going to happen is when I pull on this rope here, let's give it a force of 10 newtons. When I pull with that 10 newtons of force, it's going to cause this disc to spin. It's going to cause it to rotate. The reason it's rotating is because there's a torque being applied to it. Now, let's draw a simpler side view, and that way we don't get as much into three-dimensional things, so it makes it a little bit easier. Okay, here's my 10 newtons. Here's the pivot point at which around I'm going. This is R over here, and then I'm going to pull it here. Now, the other thing I could put on here is mg, and what we're going to do now is, in order for it to rotationally accelerate, there must be a net torque. The net torque is equal to I times alpha. What I'm going to try and find is, what's alpha? So alpha is my unknown. Now, in order to calculate I, you're going to need a formula for I. Every shape has a unique formula. In this course, I'm not teaching you what those formulas are. They're going to give you that formula. Right now, the moment of inertia is just a number. Later on, you can calculate it. For a disk, it works out to be, for a cylinder, I is equal to mr squared. So, but again, they'll give you that formula. They're not, because every shape has a different formula. So we're gonna simply calculate. Well, let's go ahead and calculate that now since we can. I is equal to 1 kilogram times r squared is 0.5 meters squared. So I simply have 1 times 0.25. I have 0.25 kilograms times meters squared. Okay, so that's my moment of inertia. Now the next thing I want to do is I want to calculate what the torque is. Well, if I look at this, the torque is going to be 10 newtons times R. So the sum of the torques, I have F. I'll write a generic equation first. F times R. I'm going to call this direction positive. F times R. Now here's the neat thing about it. mg actually acts through the center point. Since mg acts through the center point, this provides no torque. In other words, the weight of the disk, since it's evenly spaced, is not going to help cause it to rotate, and that makes life a little bit easier. So my net torque is really just Fr, and that's equal to I times alpha. Okay, now let's plug in the values. We know that F is 10 newtons. We know that R I gave you as 0.5 meters. That's equal to 0.25 kilograms times meters squared times alpha. And alpha is what we're trying to find. So this is going to be 5 newton times meters divided by 0.25 kilograms times meters squared. That's all equal to alpha. So therefore alpha is equal to, that'd be 5 times 4. Alpha is equal to 20. Okay, but 20 what? I'm going to tell you what it is. It's radians per second squared, but let me show you why. I have a newton over here. Newton is a kilogram times meters divided by second squared. I'm multiplying that times meter. I'm dividing it by kilograms times meters squared. Well, the meter squared is going to cancel out both of those meters. So that's gone and that's gone. The kilograms cancel out with kilograms, so I'm left with 1 over s squared. And that 1 is talking about radians. Remember, it's technically not probably a true unit. It simply tells you how fast something's spinning. So that's your answer. Let's look at another simple thing you could be asked. Let's take a metal rod, and we're going to pivot it around here. The rod is 1 meter long, and let's make it a mass of 1 kilogram. And what I want to calculate is what the net torque on it is, and then also use that to calculate alpha. Now, here the key thing is, the center of mass for this system, since it's a uniform object, is going to be right there. So I can treat the entire object as if it acts at that individual point. This is my pivot point. Now, the nice thing about choosing this as a pivot point is I get to ignore any forces from the pin. They do not add torque. They don't add torque. So if you can, choose a point that's going to allow you to eliminate torques. And I don't have to worry about anything. Yes, there is some force acting on this. I don't know whether it's up or to the right, but there is some force acting on it, but it doesn't add a torque since the lever arm would be 0, so it's not helping you to torque it any. Now I'm going to say the sum of the torques equal I times alpha. Now, I for rod is equal to 1/3 mr squared. Now again, you don't have to know those formulas. They will give them to you. Right now, I is just a number. So then I'm going to say alpha is equal to the sum of the torques divided by I. Now let's plug in our value. Well, the sum of the torques is going to be m times g. Well, m is 1, so this is 10 newtons, 9.8 if you want, times the distance of 0.5 meters. Because remember, if this entire length is 1 meter, this is going to be 0.5 meters. So therefore, it's the distance away from the pivot point. That's the torque. Divided by 1/3. Well, the mass is 1 kilogram. R squared is the entire length of it, which is 1 squared. So I essentially have 5 divided by 1/3. 5 divided by 1/3 is 15 radians per second squared. Now, here's one extension I can make with it. If you want, here's an extension that I can make with it. I can say, okay, what happens now if the rod is like this? Is alpha still going to be the same? Well, the answer to that actually is no. It's not going to be the same, and the reason for that is when I get to this point, that's still my mg. This is still my pivot point. And when I go this, remember, it's the sum of the torques equal I times alpha. Now, I is not going to change, but my torque actually does change. Because remember, it's only the perpendicular component of the force that causes torque. So what's going to cause torque is that. So in order to solve this, you'd have to know the angle. But realize the torque is going down. This stays the same. So therefore, I has to go down. Excuse me, alpha has to go down in that. Now, you can calculate linearly how fast these points are moving by using our bridge equation. A is equal to alpha times r. That's a bridge equation to allow you to go from the linear world to the rotational world. So the key thing is, as it happens, it's the rotational acceleration is going to be less. More on this later and in class.